Okay, it's 2 o'clock. So as usual, I'm going to use the menti.com to communicate with you. And today we are going to talk about the machine learning. And if you have any questions on the Pythons, please let me know. So before we go into the details of the machine learning, I want you to answer the other Python questions. And I hope you already know a lot of things about the Python. Okay, still students are coming, but I'm going to start because the first part that I'm going to show you is just a motivation.
Les gens y voient s'ils portent bien leur masque. C'est que tu portes un masque quand le bas de ton visage est caché. N'oublie pas de mettre un masque, s'il te plaît. On porte bien ton masque.
C'est important, on peut tous se tromper, on peut tous oublier.
Okay, this is a part of the news clip, and when I was looking at the news, I was surprised that that's not a news. That's very easy, because so today I'm going to show you how to make that kind of things very simply. So in the course syllabus, there is a web link to the teachable machine, and you may copy the URL and put it into your web browser. But let me show you what we can do with that. So its name is Teachable Machine, and it has a short video script. So let's watch it together.
People are training computers and creating machine learning models to explore all kinds of new ideas. New ways to interact.
Yes.
To understand the world. To play. And experiment. But machine learning is pretty intimidating to get into. So we've been wondering, what if it wasn't? With Teachable Machine, we set out to make it easier for anyone to create machine learning models without needing to write any machine learning code. When it first launched in 2017, it allowed everyone to get a feeling for what machine learning is all about. But now, Teachable Machine puts the power of machine learning in your hands, allowing you to save your models and use them in your own projects.
So let's say you want to build a model to recognize you versus your dog. You just open up the site, record samples of you and samples of your dog. Click Train, and you instantly have your own machine learning model, which you can use in your sites, apps, and more. You can upload your model to host it online, or download it to work entirely on device.
With Teachable Machine, you can create custom models for all sorts of things. Using images, audio, or even poses. Personalized machine learning models for the things that matter to you. And folks have already been trying it out, using Teachable Machine in their own experiments, solving problems in their communities, or even just at home. Start creating and see where your ideas take you at g.co/teachable machine.
Okay, so we are in this site, and I'm going to show you how to use this. So there is a button. I will give you a chance to play with that. So first, watch me. So I'm going to get started. And it has three different projects. So first one is image, the second one is audio, the pose, and I'm gonna use the image project. And it says the class 1 and class 2. So today I'm going to show you how to classify the human face. So for this one, I will say no mask. And then I can give some examples to the computer. So I'm going to use the webcam. And I can record, my pose. And it has 139 samples. And then for the class 2, I'm going to use my mask. So it's a mask. And then again, using the webcam, I can provide the image. And for some people, they don't wear mask properly. So I'm going to make another class. And I'm really surprised that it's really meaningful. Toxic. You see? Yeah, somebody just wear a mask on the chin. So I'm going to make this image. Okay. So I have three different categories or three different classes. The first one is the no mask, the mask, and toxic. And maybe I need to train this model. So I press the button, train model. And it says it's preparing data, training data. Okay, and so don't switch tabs. And I have to open this tab. And it is, moving. So training, it's 20 out of 50. Okay, now the training is finished, and I can use my model to classify the picture. So you can see the output. There are three categories. So one is no mask. Oh, that's the no mask. And I'm going to wear a mask. Then you can see the category is changed to mask. And if I cover just my chin, it's toxic. And you can play with that. So it's still no mask, maybe toxic. Oh, it's a mask. And I just made the machine learning program to classify 3 different categories. So actually, we can export this model to somewhere. And if you, of course, this is just me, but if you train this model for several different people with several different people wearing mask or wearing no mask, then it will pretty correctly classify that the person is wearing a mask or no mask. So even if I cover my, it's still no mask. Maybe I can play with that. So I can just cover. Yeah, then it's a mask. It's confusing. Okay. So this is how you can build a model. So I'm going to give you, say, 10 minutes so that you can play with your own experiment. So you can play with your, actually you can classify anything. So for example, the cup or the pencil or your your fingers. So maybe you can play with it, and I will be back in 10 minutes and then talk about something more. So go to the website and see what you can do. So you may also try for the audio examples, or you may try the pose example. And I hope to see how good it is. Yeah, it really works. Yeah, that's true. Yeah, lots of students, send me a heart. And it's fun. But it's fun. But some students might think that, okay, it's fun, but what are we going to do with that? And there might be an answer. I can answer your questions. And before going to the answer, I'm going to show you some more things. So first, you can add many classes. And then here is the advanced option. And if you see the advanced option, you can see some words that you have never seen. So it's epoch, batch size, learning rate, and what's under the hood. It's accuracy per class, confusion matrix, and that kind of things. And once you finish this today's class, you will understand what all these things, not all of them, but most of them, you will understand what it means. So and some vocabulary is training samples, test samples, underfit, overfit, epochs, and so there are something you need to know. So let's go back to where we can use these things. And there is a very good examples. So the first part of this video is not quite audible, so you may not understand what is being said here, but it's okay. Just watch the video and you will understand what I mean.
Google has very good general speech recognition, but if you do not sound as most of people, it will not understand you.
No one's ever collected large data sets of people whose speech is hard for others to understand.
People who have multiple sclerosis, for GF, who had stroke, who stutter.
They're not used in training the speech recognition models. The game is to record things
What's the temperature today?
and then have it recognize things that you say that aren't in the training set. Dimitri recorded 15,000 phrases. It wasn't obvious that this was going to work. He just sat there and he kept recording.
We need to make all voice interactive devices be able to understand any person who speaks to them.
You can see that it's possible to make a speech recognizer to work for Dimitri. It should be possible to make it work for many people, even people who can't speak because they've lost the ability to speak. The work that Shenxing has done on, voice utterances, from sounds alone, you can communicate. But there might be other ways of communicating.
Most people with ALS end up using an on-screen keyboard and having to type each individual letter with their eyes. For me, communicating is slow.
Steve might crack a joke, and it's related to something that happened, a few minutes ago. The idea is to create a tool so that Steve can train machine learning models himself to understand his facial expressions. To be able to laugh, to be able to cheer, to be able to boo. Things that seem maybe superfluous, but actually are so core to being human.
I still think this is only the tip of the iceberg. We're not even scratching the surface yet of what is possible. If we can get speech recognizers to work with small numbers of people, we'll learn lessons which we can then combine to build something that really works for everyone.
To understand and be understood is absolutely unbelievable.
So it may seem a very simple model, but for some people, it may really help them to communicate to the other peoples. So I think it's a really good idea to learn how these things work. So we are going to start from the first, the Colab. So copy and paste it on your web browser. Okay, so I said this is the machine learning intro, and I encourage you to save it into a different, so for example, I'm gonna change it to English. So you can save a copy in Drive. So make a copy, then everything you do on your Core app will be saved in your Drive. So first one is just a comic, and some people agree with that, and some other people will not agree with this comic. So some people say the machine learning. Some people say machine learning is just another way to express the statistics, and some people say that it's not glorify the statistics. But I would say that if you are learning machine learning, the basic start is always the statistics. So I'm going to teach you what the regression means first place. So in order to run this Core app, I need to connect it. So here, connect. Then it is connected. And you can see here, there are 7 cells hidden. And when you press this cell, you can see, something is expanded. And this arrow is collapsed and expand, collapse, expand. So I really like to use the machine learning, so I try to record this sentence with computer voice.
The concept of regression comes from genetics and was popularized by Sir Francis Galton during the late 19th century. Galton observed that extreme characteristics in parents are not passed on completely to their offspring. Rather, the characteristics in the offspring regress towards a mediocre point. By measuring the heights of hundreds of people, he was able to quantify regression to the mean and estimate the size of the effect.
So you can notice that, yeah, this is not the human voice, but I think it's quite audible, so I like it. And this is the first data that I would like to show you, and the data itself is the original, comes from the original one. So the word regression, you may know that what the regression means or may not, but the first people who used the word regression for this situation is this one, the Sir Francis Galton. And he was a part of a statistician, and he studied also the genetics. And one thing, very famous things that he discovered is that the relationship between father's height, which is on the x-axis, and son's height. And we think that, yeah, if your father is tall, the son is probably tall, and we know that, yeah, that kind of relationship holds. But he is the first one who really discovered this one, and then tried to find the mathematical relationship between these two. And then, so basically it is trying to find a line that goes through all these points. And he found something very interesting, yeah, on this line. So before we go into the details, let me show you the data set first. And it has columns. So you can see the family, father, mother, gender, height, kids, male and female. And he was actually trying to gather all these data. So he is the people in late 19th century. So he visited every family and measured the height. So you can see the family one. So probably the first 4 people are in the same family. So the height of the father is the same and mother is same. And gender means, I think, their children's gender. So male, female, female, female. So the first family has 1 male, 1 son, and 3 daughters. And they measure the height. And the kids means the number of kids in this family. And it's, yeah. So some family has 5 kids and some has 6 kids. And it's, I think it's natural, yeah, because it's 19th century. So I'm going to make a plot through these points. And it really takes some time because it actually performs the calculation for the whole data set. Okay, now we have a line. And you may think that, yeah, this is, yeah, obvious. But the reason for this line is called a regression line is that it has a special meaning. Well, later we'll see the actual slope of this line, but the important thing he found is that the slope of this line is less than 1. And that is very important because let's suppose that the slope of this line is greater than 1. So that means if your father is tall, the son is much taller. And if your father is short, your son is going to be much shorter. And if that happens, then from generation to generation, that will be exploded. So some parts of the people will be really tall, and some other part of the people will be really short. Then the human beings can be divided into two different categories if the slope is over 1. But fortunately, the slope is less than 1. So that means that's the meaning of the regression. So some extreme height does not pass on completely to their next generations. So that means people's height tends to regress to the over mean, so it says it's mediocre point, but basically it means the mean. So even if your father is tall, the son's height tends towards the average of the human being. And if father is short, the next generation tends to be taller than his father. So the human beings from generation to generations, we maintain some very similar height. So that's the thing he found, and he called this line regression. So it tries to regress to the mean. Okay, so it makes sense, but the line does not pass all points. But there is a relationship between these two lines, and we know that how can express this equation in formula. So I said, y is equal to mx plus b. So in this case, y is the son's height, and m is the slope of the line, and b is the father's height, and the x is the father's height, and b is the y-intercept. So those are the usual terminologies we know. But in machine learning, they call these things a little bit differently. So usually it is written in this form. So y prime is b plus w1 x1. But actually, I prefer to write I prefer to write it as y hat instead of y prime, but doesn't matter. So y prime is called the label. So which means which was the output. So y prime is called the label, and b is called a bias. But here the b is the y-intercept, but the machine learning people call it a bias. And W1 is called a weight of feature 1, and X1 is called a feature. So in this formula, we have just here one feature, but you may have several features. So in that case, the equation can be written in this form. So the first feature, second feature, and third feature. So if you go back to the original data set, we might predict the son's height or maybe the daughter's height with many different features. For example, the variable that is the variable that affects the height is not only the father's height, also the mother's height will take an impact on their children's height. So we may include the mother's height also. Then this equation is going to be W1 father's height plus W2 mother's height, and so on. So the terminology we are going to use is the labels. So label is Y. So Y is called label. And X is called the features. And then examples. So example is a particular instance of data X. So some example is a labeled example. That means it includes both features and label. And some are called unlabeled example because it contains features but not the label. And we are going to use the terminology model. And model is the relationship between features and label. In our case, it is just a simple linear equation, but as we develop our model, the model can be really complicated. Oh, and then, yeah, the one more thing, there is a difference between regression and classification. So regression model predicts continuous values. For example, regression model make a prediction that answers the questions like the following. So what is the value of a house in California? So the value of the house in California is a continuous variable. It can be $1,000 and or $1 million. So it can have continuous values. Or what is the probability that a user click on this ad? So yeah, there are lots of advertisements on the web. So what is the probability that a certain user click on this ad is also a regression problem. And classification problem predicts discrete values. For example, is a given email message spam or not spam? So you can classify it between two different things. Or is this an image, a dog or a cat or a hamster? So this is the classification with three different categories. So what we did on the teachable machine is actually a classification problem, not a regression problem. It does not predict your next generation's height. It just classifies whether it is a mask or whether it is a no mask. So that is called a classification problem. But the example that I showed you here, the relationship between father's height and the son's height is a class of a regression problem. So maybe we can use this data set for the classification. For example, we can draw a histogram of the male's height and female's height because we have all the data set here. So here is a height, and this height is actually the height of the children. So it may be a male or it may be a boy, it may be a girl. So if we take all these height as our feature, then we can use this feature to predict whether that person is a male or a female. Then this problem is called a classification problem. Okay, so before I go into this one, yeah, I want to take your questions. So if you have any questions so far, yeah, please let me know. Okay, so far, yeah, there might be no question because yeah, it's just an explanation of the terminology. Okay, let's play with a graph. So you can play with your graph, yeah, from here, but actually I wanna go to this website directly, and it has a wider screen. Okay, the website is called the Desmos, and it's for actually less than high school students. How to make a line, what is the meaning of that line, but we can use that. So here are 2 points, and when you move the mouse back and forth, you can zoom in and zoom out. And if you are confused, if you are lost, then here is a home button. Then you can go to the basic zoom, and you can increase and decrease. And here is a menu. So this is what I have made. So we first add 2 lines, and then I'm going to add another movable line. So you can move this line by moving these 2 anchor points. So here is my question. If we have 2 points in 2-dimensional space, and it will give you a line, and is it possible to draw a line that goes through those 2 points? And the answer is yes. So we can move it, a little bit, and then the weight of this line is here 0.46, and the bias is 0.01. Of course, if you move the points, then you have to do it again to find the exact lines. So there is no problem if there are 2 points. But my question is, if I add third point, so I have 3 points, and I want to make a line that goes through all these 3 points, and it is impossible unless that they are all on the same line, right? So this is a very rare case, and it's not interesting. So if the other point is here, then how can I find a line that goes through all these 3 points? And that's impossible. So instead of finding a line that goes through all these 3 points, I want to find a line that fits these 3 points best. So here is my statement. I want to find a line that fits 3 points best. And I make emphasis on best, because what's the meaning of a best? So what is the best line? So maybe some might argue that, well, I can cross 2 points, so this is a best. But we usually think that this is not the best. So in order to define what is the best, then we need some sort of a measure of error. So when I press this button, you can see lines, and that's the error between my line and these 3 points. So if you move your line, the errors are changing. So what I mean by best is that to minimize the error of these 3 points. But the problem with that is that if I think about the error only, so here is E1 and its number. I don't know which one is Y1 or Y2, but the 2 numbers are positive and the other one is negative. So that means if I move a little bit strange, I can probably make it as 0 by adding these all 3 numbers. But that's what I want. I mean, I can make it 0, but as some slope and intercept, some errors are positive and some errors are negative, so it will be canceled to each other. So instead of the cancel to be each other, I want to make it a square. So I can make a square of these 3 points. So the first one is E1, E2, E3. So you can see E1 squared, E2 squared, and E3 squared. And then since there are 3 points, I'm going to make an average of these 3 points. So it'll be appropriate. It'll be appropriate to decode this quantity as mean squared error. So my goal is to find the minimum of this mean squared error by moving these lines, but it's not easy because first of all, I don't know what is the minimum value of this mean squared error, and because it is done by hand, I have to play with it several times. So instead of spending too much time on this, I would go to the computer program to find the value for the best line. So I'm going to implement the regression line from scratch with NumPy. So we already know what NumPy is, and we know how to we know how to deal with the Python and NumPy. So the first cell, I'm going to import the most important 3 libraries. So import NumPy and import pandas and import matplotlib.pyplot. And then my data set is somewhere on the internet. I saved it on the internet. And then I can use the pd.readcsv to read my data set, and I'm going to call it df. So in order to run this cell, you can either press this play button or shift enter. And then it's done. Okay. Then I'm going to show you how to use the scratch mode. So when you go to the menu, under the insert menu, there is a menu scratch code cell. And if you press this one, you will see on your right hand side, there is going to be another cell. And this cell reflects everything up to your current executed cell. So for example, if I write df and press shift enter, I can see all the data. And here, I want to take the father's height, and I want to take the son's height. So we are going to use the filtering. So for example, okay, in order to select the son's height, the first thing we need to know that the son's gender is male, of course. So I can say that its gender is equal to male. Then it does not work. Yeah, it does not work because I made a wrong comparison. Yeah, this is the correct one. Then I can get true and false, true and false, and I want to get the father's height with this true and false value. So it's df Okay, it will gives me all the data set with the male. It's wrong again. Yeah, I just need the one. So you can see the index is 0, 4, 5, 8, and it has only 460. So that's because about the half of the people are son and half of them are daughters. So I can take that male, and then in order to get the father side, I need to write it as father. Then this is the data set that I can get. So I set this value to X, that's the father's height. And then this one is the son's height. Or maybe you can, use different things. So the Galton did it for the son, but so I'm gonna do it for daughter. Okay, so instead of using this one, so I'm gonna change it to female and female. And I have never done this before, so I wanna see it. So we define X and Y, and then see what's inside the X. Okay, the total number is different. It was 460, now it's 430. So the number of female are less than the number of male. And you can change, you can see the shape. Okay, so this is the good point that I explained what this means. So you may think that this is something wrong because it has an open parenthesis and closed parenthesis, but it has just a 1 comma here. And actually, this is a tuple. So we know what the list is, what is the number is. List is something like this. It's 1, 2. This is a list. And I said, there is another data type, and that data type is a tuple. So how can I make a tuple? So basically, you may think that this is the way we can make a tuple. So instead of the bracket, we use the open parentheses and closed parentheses. The reason why this is important is that, we may say X, make a list and print A, and I'm going to change the contents of the index 0 and then print it again. Then you can see the first list is 1, 2, and since I change it to 100, the second one is 100, 2. But if it is a tuple, then there will be a problem. You see? So it's okay for the first print statement. It's 1 and 2, but on the third line, the tuple object does not support item assignment. And actually it means once tuple is made, you cannot change the value of a tuple. So you cannot change the value. You just have to keep it as a tuple, and we do these numbers. So that's the reason why we use tuple for some cases, because sometimes we want our variable cannot be changed. So for example, this case, X shape, is this number, but if it were saved in a list format, then in the programming later, I might change the size of the shape, but that's not, I don't want that to be changed forever. So, so it might be a good idea to put it in a tuple. So if I made a mistake to change the shape of the X, it will automatically shows me that's an error. So before get into a bigger trouble, I can fix my problem. So that's the reason why we use the tuple. So it's okay to have 2 or 3 values in a tuple, but if I have just one number, then I think I have to use it in this way, but it's just a number 1, not the tuple. So in order to say that this is a tuple, I have to add comma here. So at first it looks very strange, but this is the way the Python define a tuple. So if you have just one element, then you have to add comma at the end. Then it's a tuple. Okay, so with X and Y, I change it to a NumPy array. And in the previous note, it was written in this way, but I said I prefer the Y hat. So I'm going to make a model. And this is a very simple model. So the X is father's height. And I'm going to give any number, say here 1.5, 1.2. And then for the intercept, I can give, say -3. And I claim that this is my model. So I can get, Y hat. So let me see what I get here. So Y hat is a bunch of predictions from my model. And what we wanted to do is to minimize the error. Then how can I minimize the error? So the Y hat is my predicted value from my model, and Y is the real value of the height of daughters. So maybe I can say Y minus Y hat. Then you can see, there are lots of minus signs. And if I change my model, then I would have some minus sign and some plus sign, but I don't want it to be the natural value. So I want to make it a square. So how can I make a square? So I can make it a square like this. And the everything is a positive number. And I want to take the average of all these numbers. That's the meaning of the mean squared error. So if there is no NumPy, then I have to write the for loop and add everything and divide by the number of observations. But NumPy has a function called npmean. And it gives me just one number. So that is the average of all these numbers. So this is the mean squared error. So probably I can define a function. So this is the way we define a function, def, and my function name is myLoss, and it takes 2 inputs. So one is the actual daughter's height, and the other one is the predicted value from my model. And then it returns this value, npmean Y minus Y hat squared. So let me test what it gives me. So maybe I can say my loss and y hat, and it gives me 266. So my goal is to find the weight and bias that minimize this my loss. So that's my goal. So how can I find it? Well, first I'm gonna use a very brute force method. So I'm going to search every possible values for the intercept and every possible value for the slope so that I can find the appropriate conditions. So in order to do that, we need to know something about the range function. Okay, so range function is pure Python function. So range 10, it does not show me the numbers, but if I wanted to verify what's inside, I can use the for loop for I in range 10 and print I gives me from 0 up to 10, and 10 is the 10 is excluded, so I can get from 0 to 9. And if you want value from 4 to 10, then you can change it in this way. Then it's 4, 5 up to 9. And if you want the 4, 6, 8 something, then you can add another step. So this one is the increment, and it gives me this one. So at first I was planning to use, okay, I know the range function, so I'm going to search the slope from, say, negative 10 to positive 10 with 0.1, and it gives me an error because the range function, the original range function, cannot take the float value for the step. But NumPy provides a more general way. So I'm going to use the np.a range. So it's not a range, it's a range. So it's the name is different from the range, but it's np a range. Then it is possible to write from 4.1, 4.0, 4.1, and so forth. So here I write a for loop. So W is going to be changed from 0.5 up to 1.5 with the increment of 0.0. So it will be 0.5, 0.6, 0.7, 0.8. And within that for loop, I'm going to change the bias B from -1 up -10 to 10. So you can see that every number will be changed. And with this W and B, I'm going to make my model. So my Y hat is changed. My hat will be changed for every possible value of W and X. And I'm going to print out the W, B, and my loss. So let me run this one, and it gives me a long list, but we can see if my W is 0.5 and if my B is -10, then my loss is this amount. And if I change my bias to this number, then this is my mean squared loss. And you can see the mean squared loss is changing. And since this is a brute force search, I have to find the minimum by just looking at all these numbers. So it's just 45. Oh, it's possible. 45, and some are 13, 9, 6, 6, 6. I think this is the best one so far. So weight is 0.9 and bias is 1. Bias is 2. This is the best one I can see so far because the mean square error is 6.19. So I think that's the best. Oh, there is another one. It's 0.8 and 9 is better one. Okay, so this is very rude. It's very brute force, but I can find it's 0.8 and 9. So I can make a plot. It's 0.8 and B is 9. And this is a plotting function, but you can you will have no problem to understand what it means. So I'm going to make it, and you see the graph is a little bit different from the son versus father, but still there is a positive relationship between father's height and daughter's height. Okay. Any questions on this so far? Okay. Can you make a code to find the minimum error without having to find it manually? Okay, that's what I really wanted to do. So we are going to do that. But here, I wanted to explain it from the very beginning, just one by one, so that you can understand the basic things. So we are going to make a code to find the minimum error automatically. So that's a good question. Okay, that's good. Then I'm going to say about just 5 more minutes, and we are going to take a break. So now you understand the basic mechanism of the regression analysis, and then we, in order to do that, we did lots of things here, but actually it can be written just this code, just 5 lines of code. You can do everything, and that's the power of the TensorFlow. So let me read that. Let me read this one. Okay, the first one is import something. So in order to use TensorFlow, we need to import it. So import TensorFlow, and we are going to call it as TF. And then we need to make a model. So here I made a model with the simple linear equation like this one. And I knew that I'm going to change the W, I'm going to change the B, but we are going to, we should have the ability to use many different kinds of models, and TensorFlow gives us that ability. So it looks a little bit strange at first, but I will explain you what it means. But this dense layer is exactly what we did. So TF-Keras model sequential and TF-Keras layers dense, just take it for granted for a moment. And this is the way we build a model. And then even if we have a model, we need to define a loss. And the loss that we have used is the mean squared error. So in order to use that loss, we need to tell the model what is my loss. So this is the way to tell the TensorFlow what kind of loss that I'm going to use. So it's model.compile, and I'm going to specify the name of the loss. So loss is the MSE, mean squared error. And then instead of writing the for loop, so here we have a for loop. We just put X and Y, and then how many times we are going to do this for loop. This is the meaning of the fit. And then once we have the fit, then we are going to predict. So let me see what, so once you understand these 5 lines of code, then you can understand the whole rest of this final one. Because at the first 4, it's just to import the libraries. So import the TensorFlow, NumPy, Panda, and Matplotlib. And we are going to read the data file. And then we take some parts as our X, and we take another part as our Y. And then these 3 lines, are the main core of the TensorFlow. So first line, I define the model, and then I let the model know that what kind of loss that I'm going to use. And then I said, okay, use the X as your X variable for your feature, and use the Y for your label. And then epochs means how many times you are gonna repeat this one. And then once we finish the training, then we can get the value for the W and B, and then use this value to plot. So I'm going to run this one, and you will see it will be executed 1,800 times. Purpose is force, okay. I'm going to make it true so that you can see what's going on. So it calculates 180 times for us. And you can see the loss is decreasing. No, not that much, but it is still decreasing. Still 1,020, 1,200. Yeah, we are almost done. Yes, we are done. And the finding W value is 0.95, and the slope, the bias is 3.14. And this is different from the father and daughter's data, because here I use the father and son's data, and this is the graph of the result. So here we do not write the for loop, we just use some TensorFlow code so that the machine can, we say it learns, but yeah, we can make the machines to produce some result. Okay. Okay, I have a question. Okay, epochs 180. So here, this brute force search, I change my W value from 0.5 up to 150, and then I change this V value from similar to similar. So epoch 1, so one epoch means if you use the whole data set once, then that's the meaning of the epoch. So 180 means I use whole data set to calculate the movement one time, and then I use that for another time, and 180 times. That's the meaning of the epoch. And I'm going to tell you a little bit more of the epoch once we take a break, after the break. So just wait for a second. And we are going to take a break. And we are going to start at 3:25, just 7 minutes break. And I'm going to talk about it more than this. So if you have questions, just put your questions here, and when I will be back, then I will answer your questions. And by the way, you may ask question in Korean. You don't have to write it in English. Okay, it's 3:25. So yeah, the epoch is at first is a little bit confusing, but basically you may think that epoch is the number of for loops. That's the basic understanding of the epoch. And then the students ask me that what if there are more than 2,000 epochs? And that's true. The minimum value can be decreased, but it can be decreased or cannot be decreased. So we have to decide how many epochs we are going to use. So, okay, right now you may not satisfied with my answer, but you will see why we have to decide the number of epochs and how it depends, how it will affect the accuracy of the models and so on. And we can actually see the meaning of the epoch already. So let me go to our first teachable machine example. And for the advanced setting, here is epochs, and it uses only 50. And if you remember, there are lots of pictures on the class 1 and another lots of pictures on the class 2. And the one epoch means use all the data sets. So for example, in class 1, there are 100 examples. And in class 2, there were another 100 examples. And in total, we have 200 examples. And the epoch means if you use those 200 examples once, then that's the one epoch. And 50 means use those 200 examples 50 times. That's the meaning of the epochs. And we know what is the meaning of the examples and what is the meaning of the features, what the label is class 1 or class 2. And so it's, yeah, we know a little bit about the machine learning. Okay, why does error decrease over time? Isn't the model repeating the exact same procedure again and again? Actually, no. So this is the topic that I'm going to talk. So how can we find the minimum? So I'm going to explain, yeah, from now on. So let's copy to the second collab. To here. And it says descending to machine learning, and I'm going to make a copy. And then change it to English and connect. Okay, this is the picture we need to understand. So I took this picture from the Wikipedia. So we use the word training. So remember, it's train the model. So what does it mean by training? Training a model simply means, actually, I prefer this one, determining good value for the weights and bias from the labeled example. So training means trying to find the W and B. That's the meaning of the training. And in the previous exercise, I show you how to use the brute force method. So I changed the W from some value to another value, and I constantly change the B values so that I can find the minimum by just manually looking at all those numbers. But we can use a better way to train the model. So in order to train the model, first we have to think about the loss. And in our case, loss was the mean squared error. So loss is a penalty for the bad predictions. That is, loss is a number indicating how bad the model prediction was for a single example. So for example, if model is perfect, then the loss is 0. And otherwise, the loss is greater. So the goal of the training is find a set of W and B, and in some cases in most cases W's are W's and B's are numerous. So find a set of weights and bias that have low loss on average across all samples. So we have seen this example. So I said the difference between the actual value and the predicted value, we will call this one, these are error. So error. So we are just trying to find the mean squared error. And this mean squared error is the most popular error for the regression problems. And in mathematical notation, it can be written as this. So mean squared error is the average squared loss per example over the whole data set. So to calculate the mean squared error, sum up all the squared losses for individual examples and then divide by the number of examples. So here, y is the true value. So for example, with the sun's height. And prediction of x is a value from the model. So of course, it depends on the choice of the W and B. And then we take the difference and square it, and then sum over all the value and divide it by the number of examples. That is the mean squared error. So although the MSE, the mean squared error, is commonly used in machine learning, it is neither the only practical loss nor the best loss for all circumstances. So in the traditional statistics, for the regression problem, the mean square error is probably the most important measure. But for the machine learning problems, we use the mean squared error, but sometimes we use different measures. So here is the how can we reduce the loss. So this is the very simple example. So suppose that we have a model of this, model of this, and then we need to start some point to start with. So we just simply set b is equal to 0 or w1 is equal to 0. And then you plug in this number into this model, and then your prediction, y prime, is going to be 0. And then from this prediction and the correct value, you can calculate mean squared error. And then from that point, based on some mathematical method, we can move on to a next point, next set of W and B. And then from there, we can calculate the mean squared error again. And then we move on to the next point, until it converges to some value. And that secret is called the gradient descent. Okay, so I'm going to show it in a wider screen. Okay, here is the setup for explanations, and don't worry about the next two lines. So you don't have to worry about these two lines. So here I take, for simplicity, take the x as -1, 0, and 2, and as y negative 0.5, and 0.5, and 2.5. And then we can make a model. So that model is here. So it's from the X data. And then I can choose my W and B at first. So maybe I can choose, this one. So this is my choice for the initial value. So here, you can see this value here it's W is 3.24 and B is 2.42. And from this Y hat, we can construct the mean squared error, the shape of the mean squared error. So that's the reason why I show you on the very top this picture. Actually, mean squared error is actually the negative of this one. And in order to understand what it means, you can think about the X as the weight and B as a bias. And then Z is the mean squared error. So for example, yeah, if your X is some value, so I mean, yeah, your weight is some value and your bias is some value. And from your weight and bias, you can calculate the mean squared error for the whole example. And that will be a point around here. But actually, it is very hard to draw this three-dimensional graph. So instead of drawing a three-dimensional graph, I make it a contour plot. So here, the outside is the biggest, not the biggest, but yeah, from this picture, the outer circle is the biggest mean squared error, and then smaller, smaller, and smaller until we reach the minimum point here. But the problem is, we actually do not know the shape of this mean squared error function. We just can calculate the mean squared error at some specific point at a time. So for example, at this point, the mean squared error is 17 something. So if I move my point, you can see my mean squared error is changing. So if I move to close and close to this one, it's going to be a 0. And actually, if everything is perfect, the mean square error should be 0, right? Because everything is squared, so the minimum value it can have is 0. But we don't know how to move. So in brute force search, what I did is I just moved my W value, one here, one, the other one, and up here, and then change the B value. So I calculate all the numbers here, and then manually find, well, this might be my minimum. That's what I did. Oh, okay, here is the real 3D plot of the mean squared error. So actually, it is in this convex form, and there might be there is only one point, which is a minimum, but we do not know this minimum point. So we are going to learn the gradient descent method. So this is just the same thing. And you may wonder, what is the gradient? Okay, let me write something here. And I really hope you understand the differentiation. Let me start with a very simple one. Okay, y is x squared. What is the derivative of y with respect to x? It is written as this, and then the answer is 2x, right? And even if you don't know how to calculate the derivative, it's perfectly okay, because it is just a conceptual thing, and you don't need to differentiate anything in your computer program. The TensorFlow will automatically differentiate everything for you. So you just need to understand what is a derivative, and you don't have to know how to calculate the actual derivatives. So you just need to know, the meaning. So this is for the one example case. I mean, one variable case. But here our problem is actually looks like this. The mean squared error is 1 over n summation y minus y hat squared. So in other words, it's 1 over n summation y is a value, and y hat is a value from my model, and my model was this one, w1x plus b squared. So what I wanted to do is to this notation is called the partial derivative. Don't worry about it. Yeah, you don't have to know what partial derivative is. It is just a motivation that you have to take the calculus course, and you have to take the linear algebra course. So you can take the derivative with respect to x, and you can also take the derivative with respect to b, because x is a variable and b is also a variable. So you can take the derivative with respect to this. I don't know, yeah, we can calculate it, but yeah, it's not important at this point. And in this course, we just need to know what's the meaning of these partial derivatives. And once we calculate this, question 1 and question 2, then we may write it in vector form. So question 1 is question 1 and question 2. And this vector is called a gradient. So gradient is nothing but a vector. It's called a gradient. So it's just a fancy name. So since we have two variables, it's a two-element vector. But if our parameters are getting larger and larger, we have lots of long vector, but it's just called a gradient, and it indicates where is the direction that your value will be increased. That's the meaning of the direction. And do you remember the meaning of the derivative? So in a graph like this one, you can calculate the derivative of it at this point. And let's say this is, okay, this function is x squared. And you can say the derivative is 2x. And if x is equal to 1, then it is going to be 2. That means if you move 1 to the x, then your function is going to be increased by 2. So that's the meaning of the derivative. So there is lots of formulas, but I can show you the derivative here. So if your point is here, this is the derivative. And this derivative shows you the direction and the amount of increase of your movement. So that means if I move from here to here, I'm going to move this point from here to here, but as I move this point, the gradient will be changed. So you just think about that is, okay, I'm gonna move it here. And you can see the gradient is it's larger than the previous one. And if I move to this way, then it's even much larger. So the first lesson you can learn from here is, in order to find the minimum, you have to go to the negative sign of the derivative, negative sign of the gradient, not follow the positive gradient. So I can do it in a graph here. So you see, this line now, actually this line is just negative of this line. So one shows you the real gradient, and the other one shows you the negative of the gradient. So I'm going to turn off the real gradient. So every point here is the negative of the gradient. So if I move in this direction, you can see the negative of my gradient will be changing. So how can I move? Okay, let me make sure. You don't have to know how to calculate the derivatives. You don't have to know the actual calculation of the gradient. You just need to know the meaning of the gradient. And in order to minimize the loss, we always follow the negative of gradient, and that negative of gradient is here. But one problem with that is that, okay, I can start from here, and this is the direction and magnitude that I can decrease my loss function. So I move it here, and then it says, oh, I need to move it here. So if I move it here, then it says I need to move it here. And every time I move it there, the direction is getting bigger and bigger. So the first lesson was to take the negative gradient, and the second one is do not take the full step. Just take the smaller of the total step. So that's the meaning of the learning rate. So here, learning rate is 1, but I'm going to decrease the learning rate. So as I decrease the learning rate, as you can see, the magnitude of the gradient, the negative gradient is reduced. So here I'm going to reduce it much larger. Say 0.2. And let me try to solve this problem here. Okay, I'm very away from the minimum point, but it says I need to move here. So I'm going to move it here. Okay. Now I need to move it here. So I'm going to move it here. And then it says I need to move it up to here. So, okay, I move it here. And then next point is here. So I move it to here. And next point is here. So I move it here and here, here. And then finally, I arrived. The mean squared error is 0.004 point something. So that's the way I find the direction. Got it? So this is a manual. So at some initial point, I need to calculate the direction. I need to calculate the gradient, but the TensorFlow will do that for me. And then just take the negative sign, but do not take the full step. Just take the smaller, than the full step. And that will be called a learning rate. So all those things are explanation for this. And the one more thing that I wanted to talk is called the stochastic gradient descent. So I hope you understand what it means by gradient descent. But there is one more term in front of the gradient descent. It's called stochastic gradient. And I'm going to read this part. In gradient descent, a batch is the total number of examples we use to calculate the gradient in a single iteration. Okay, so in my example here, I showed you my x is 3 points and my y is 3 points. And if I use all those 3 points, okay, let me say it in this way. So I say that in this case, my batch consists of all these 3 points. And then using all these 3 points, I calculate the next movement, I calculate the next movement, I calculate the next movement. But so far we have assumed that the batch has been the entire data set. So in my case, I said, all 3 data points. When working at Google scale, so Google scale is a very large scale, data set often contains millions, over hundreds of millions examples. So that means I started with 3 data points, but actually it was 3 trillion data points. And in order to calculate one step, I have to calculate 3 trillion data points. And that might be a problem. So, and furthermore, Google dataset often contain huge number of features. So my X is not just a one column, it might be X1, X2, X3, X4. So it's too big to calculate. So instead of using the whole data set, we may say that, okay, I'm going to take my batch as size 1. So that's the meaning of batch size 1. And in my example, I might not use all of them. I might use just 1. Not all of them. I think this is right. Just it's too big to be a nice graph. Okay, but okay, let me add some more. It's 1 and say 0.5. Okay, now you can see the shape has been changed because I used just 2 points. So in order to be complete, you have to use the whole data points to exactly calculate the shape of the mean square error. But in worst case, not the worst case, but in extreme case, you can use just 1 data point to calculate your mean squared functions. So that's the 2 extreme case. So one is that your batch contains all of your data, and the other extreme is to take your batch to be a size of 1. Then if your batch has a size of 1, then in order to use, say, 1 million data points, your epoch is your data, you calculate the size of batch, you use the batch of size 1 million times, then that's the end of one epoch. But if your batch size is 1 million, then use your whole data set just once is the meaning of the one epoch. And stochastic gradient means sometimes it's okay just to use a smaller data size to reach the minimum instead of using the whole data set. And that's the theoretical, there is a theoretical explanation why you don't need to use the whole data set. So you just use a very small fraction of your data set and then move to your points, and then use another small data set and then move to the next point. And still you can get the minimum point. So that's the meaning of the stochastic gradient descent. Okay, now let me go to our example here. Now we understand much of the thing here. So batch size. Okay, let me do it again. So this is my hand, and then I'm going to add, say, this is my pen. And I have 82 image samples. So there are 82 data points here. And for the class 2, I have 70 data points. And then I train it. Now it is training, and it takes the 16 out of 82 or 70. So that's the one batch. And then it calculates the mean squared error, not exactly the mean squared error in this case, but something similar to a loss, and then move it to another point to find the weight and bias and move to the another point. But you cannot divide 82 exactly by 16. So it might be, there might be a small fraction at the end, but that's okay. So once you finish your the whole data set once, then that means your epoch moves from 1 to 2. And then do the same thing again for the next epoch, do the same thing again for the next epoch until you reach 50 times. And here is a learning rate. And learning rate is the amount you are going to use your gradient. So it's the default. And as you will see, the very critical point is actually the learning rate. So if I change my learning rate as, say, 1 point, well, let's say it's 1, then probably it's not as good as we were we have seen. Okay, let me see. You see, class 1 is a hand and class 2 is a pen, but it is not responding because with this amount of epochs, it does not reach to the minimum, so it's useless. Then we can think, okay, what is the best learning rate? And actually, there is no answer. It's trial and error. But usually, if you then you may think that, okay, the bigger learning rates does not converge to a minimum point, so maybe we can try a smaller learning rate. that's a good idea, but as you can see in this example, if I change my learning rate very small, then I'm going to make it a little bit bigger. Then it takes long to move that point because I move a very little step, one at a time. But if I increase it too much, then I may not reach the minimum point. So that's the trade-off between choosing the learning rate. If your learning rate is too large, then you cannot reach the minimum. If your learning rate is too small, then it takes too long to reach the minimum. But in either case, there is no way to see whether it is a minimum or not. So we have to see how my loss is decreased, and we need to check whether we need to decide how many epochs that I'm gonna use. So in general, the larger epochs will give you a better result, but in some cases you have to limit the number of epochs, and there is another reason why you have to limit the number of epochs. So I think that's pretty much the basic introduction to the machine learning. So in summary, you need to know the terminologies of the machine learning, and then you need to understand what is the loss and how we can try to minimize the loss using the gradient descent, and what is the meaning of the learning rate, and what is the meaning of the epoch, and what is the meaning of the batch size. Of course, the meaning of the batch size or epoch will be, we will revisit that concept later once we are using the TensorFlow more extensively, but at least you need some sort of idea on what those things are meaning. Okay, let me take your questions. So we say that with a smaller learning rate and larger batch size make the training more accurate. Yes, that's true. So if you really wanted to get the minimum points, you have to reduce the learning rate. And that's true. But that takes a very, very long time. So it may take several weeks to learn. And the larger batch size means it's very similar to the whole total examples. So it will give you a better estimate, but it will also takes a very large amount of time. So yeah, you're right. Smaller learning rate and larger batch size makes the training more accurate, but it makes your training really, really long. And anyway, you understand, very exactly, what I'm trying to say. So this is a very good question. Okay. Okay, any other questions?